All right. Hello, everyone. It's our great pleasure to be here today. I am Lister, and I am with my partner, Jesus. So I'm going to start with a self-introduction. I am currently a junior studying in University of California, Berkeley. I'm double majoring in astrophysics and applied mathematics. And then I'll pass on to Jesus. You can give yourself a self-introduction.
Good evening, y'all. My name is Jesus Martinez. I'm also a student at UC Berkeley. I'm currently studying astrophysics, as kind of implied by the presentation here. And it's a pleasure to see you all here. We hope you all can learn a little from us. Maybe we can learn from you. All right, Lister, you can go ahead and start whenever you'd like.
All right, awesome. So we can go ahead and get started. Today we're talking about fantastic exoplanets and where to find them. All right, next slide, please. So before we talk about exoplanets, maybe we should really start by talking about what planets are. The most accurate definition of planets should really be simple. That is, planets are just cold, dense sphere. They don't have the nuclear fusion going on in their center. That's why they are failed stars, as we usually call them in astrophysics. So there are two types of planets in our solar system. Our solar system consists of majorly rocky planets and gas giants. But there's something else out there. So I'd like to start off our journey by first introducing to you guys some of the very intriguing exoplanets. All right, so on the left, you guys can see that's Kepler 186f, and that's the first exoplanet discovered in the habitable zone. So what habitable zone is basically this zone in which planets' orbits are in, and those planets, if those planets falls into that particular orbit zone, there's a possibility that there's water on the planet and it may have the potential to host life. On the right, we have Kepler 16b, which is the first exoplanet discovered orbiting a binary system, which the whole star of this solar system is a binary star. It's basically two stars orbiting each other, and the planet orbit around those two stars, which is a very intriguing phenomenon to see. All right, next slide, please. And then on the left, we have this first ever hot Jupiter ever discovered. And its orbit, this hot Jupiter orbit its star every 4 days. And this is really a revolutionary discovery, because previously people think Jupiter, like gas giant like Jupiter, really shouldn't be orbiting a star at such a close distance. But hot Jupiter right here really revolutionized astronomers' notion about where gas giants can be. And on the right, we have the first directly imaged multi-planet system, which this is obviously discovered through direct imaging, and Jesus will be talking about this type of exoplanet detection later on. All right. So surprisingly, the most abundant type of planets in our universe are not rocky planets, not gas giants, but somewhere in between. Usually we call them sub-Neptunes and sub-Earth, and they're everywhere. So on this picture on the left, I hope you guys are not scared by this diagram. It's a really pretty diagram, but I'm here today to let everyone know that everyone can read a scientific graph. So usually scientists start by reading the axis of the graph. So on the x-axis, we can see we have planet mass in units of mass of the Earth. On the y-axis, we can see the planet radius, which is measured in the radius of the Earth. And we have rocky cores with atmosphere, which is, as we can see on the graph, which is HIP 116454b, around over there. And we also have planets with rocky cores on the blue line, which you can see towards the bottom left. We have Venus and Earth on the blue line. But there's a lot of things in between. If we can see the diagram on the right, around 2.5 to 3.0 Earth radius, that region, if you can point your mouse to the right, that region, we can see those kind of planets are more massive, are slightly more massive than the Earth, but their radius are huge. They're like, maybe they're like 3 Earth masses, and the radius are like so many times larger than the Earth, which means those planets have a really puffy atmosphere that really puffs those planets out. So these type of, we usually call those type of planets sub-Neptunes or super-Earths, and they have stellar-centric distance, which means their orbit distance, how far away from there is the planet to the center of the star, which is usually 0.1 to 1 astronomical unit, and they're usually 5 to 10 Earth masses, and they're usually 2 Earth radius to 4 Earth radius. All right, so I'd like to go in a little bit to talk about the planet interior, like what's going on in the interior of those exoplanets. So we compare this with the three planets that we're usually well known to the left. So on the further left, we have Jupiter, which is usually metallic hydrogen plus helium. So they're gas giant, and their outer envelope is majorly consists of H2 and He, which is and helium. And for Neptune, there's Neptunes have a rocky core, unlike Jupiter, and on the outer envelope they have a fluid layer, which usually consists of ice. That's why they're usually called ice giants. And on the outermost atmosphere, we have molecular hydrogen. And for Earth, it have a solid iron core and a fluid iron core on the outside, and then lower mantle and then upper mantle. So very different constructions for these three types of planets. So what does super Earth have? So on the right, it usually have a silicon mantle. It usually have iron and nickel core, and then a silicon mantle outside of it. And there's usually a type of liquid surrounding that, and then on the outermost is hydrogen and helium. So it's sort of like Neptune, and it falls between the category of Neptune and the Earth. That's why those planets as we call sub-Neptunes and super Earth are super intriguing, because it's a type of interior that we don't really see in our solar system. Right, next slide, please. And then what the interior tells us is how the heat transfer being carried around in the planet, which our astronomers love heat transfer, because we can see how a planet radiates its temperature, and if the temperature can be potentially habitable to life. So on the left side, we can see an Earth-like planet. It usually have a conductive, in the innermost core, it's conductive. So conductive basically means, say if we're cooking a steak, and then you have a steak on a pan, and then the steak is closely touching the pan, and then the particles in the steak and the pan would randomly working to transfer the heat. So that's what it means by conduction. And on the outermost, there's convection, which usually happens in liquid, but it's not limited to happen in liquid. That the most classical type of convection we have is, say you're boiling a glass of water, and you have very cold water on the surface and hot water in the bottom, and then the hot water becomes less dense as it being heated up and rises upward, and then the cold water goes downward because it's more dense. And then through this kind of liquid exchange, the heat is constantly being exchanged. And then on the uppermost layer, we have convection and then radiation. Radiation, which is radiation is a type of method that Earth radiates its energy to the space so that we are not overheat on Earth. And it's mainly conducted through photons, the random walk of photons. But and on the right-hand side, we can see super Earth is really similar to an Earth-like planet in terms of heat transfer. So it has a rocky core and a convective layer and a radiative layer. And then a convective and radiative layer usually have a radiative boundary, which is approximately 2 times radius of the core. And this type of super Earth radiates its energy through its outer envelope to the universe as well. So that's an overview of how heat is being transferred in the super Earth. So that brings the end to my part. I am welcome to hear any questions from you guys toward the end. And right now I will pass on to Jesus.
All right. Good evening, y'all. Now, I think I already introduced myself, but yes, I'm Jesus, and we just went over a little bit on, what planets really are, and like the different types that we see. But I think one big thing that a lot of us wonder is like, okay, we know the planets exist. How do we find them? It's kind of like we know there's treasure underwater, but how do we find the treasure, right? So we're going to go over a little bit on how we find these exoplanets here. So we'll start off so there's 3 main methods here that we're going to be analyzing. These are kind of big words, I'm sorry, but one method's called the radial velocity / Doppler shift method. The other one's called the transit method, and the third one we're going to look at is the visual observation method. So unfortunately, I'm not going to go through them in order that I wrote them, just because the difficulty is a little different for each one. But these are the 3 main methods we're going to go over. There is an additional one I can get into if you guys would like at the very end, maybe during the Q&A session. But I felt like that one was a little more complicated for a general audience. That's why I left it off. But we can definitely go over that if you all would like. Either way, let's move on to this first one we got here. So visual observation. This is the easiest way to find a planet. You just look up at the sky and you take a look. All right, is there a planet up there? Is that a star? You can usually tell if it's a planet or a star because typically a planet or a star, when you look up in the sky, is going to be it's like blinking, right? It's like twinkling. It's like that song, "Twinkle Twinkle Little Star," right? So if you see something in the sky that's twinkling, that's probably a star. But if you see something that's not twinkling, it's probably a planet or a UFO. But I'm pretty sure it's going to be a planet on average. But yeah, these methods in which we can find these planets is by, looking at them ourselves, or maybe looking through a telescope, as seen here in this image, in this picture here, this little guy looking through a telescope. Or some people actually take pictures with their telescope. So they put their phone on their telescope and take a nice little picture. And if you take a lot of them, you could even, over time, you can see kind of, a planet would probably move across the sky as opposed to a star. It's really great stuff, but it's very limited in how we can use it because this tends to only really work for planets nearby us, like the ones in the solar system. We want to know about exoplanets. So how do we find exoplanets? Before we get into this, though, I just want to show this. This is an image. This won't happen on every sky that you look at, but sometimes when you look up at the sky, you can see these, these various planets distributed in the sky. Here we got the moon. Well, the moon's not a planet, but we got the moon you can see in the sky. We got Venus here, Mars as well, Saturn, Jupiter. These are all planets you could actually see just by looking up at the sky without a telescope, and it's really beautiful when you can. I think I've only got to see Venus though, but they're really good stuff. Hold on 1 second. Sorry about this. Yes. Okay. Gotcha. These are kind of pictures you can probably take if you use your telescope or something. But we got Saturn on the left, Jupiter on the right. So how do we look at these planets themselves? We use something called direct imaging. So this is kind of like looking at these planets by kind of covering up the stars. You can see here, if you look at like a light bulb, there's a little speck on here that's like a flea. It's kind of hard to look at. Although if you cover up that light bulb, you can kind of start seeing the flea, which is kind of what we do with these when we take pictures of the sky. And seeing this animation I'm about to show you here, we have this star right here, as you can see, very bright. But as soon as we cover it up, we're going to do something really special here. Let's take a look. In here, we cover it up, and look at that, something pops up in the back. The reason why is because once you cover up the brightest thing, you can now see something that's a little less brighter, which would be a planet. And we use this in, oh, sorry about that. That was an accident. Yeah, so as you can see in the animation, we'll see it again one more time, just so you can, I guess, get the feel for it. And yeah, so you can see the planet nice and great. And that's kind of how we look at these planets. And actually, we have some future telescopes we're going to be launching, which will help us with this. Like this telescope here, you can see. So the plan with this telescope is we're essentially going to put like a fan in front of it. As you can see, this thing extends and opens its arms out, kind of to block out any like really bright stars. So we can then use the telescope on the right here to see the planet a lot better. It's kind of like a shade to block when you're looking at these planets. We're trying to find these planets. My apologies. This next method we're going to take a look at is the transit method. So what's the transit method? This looks really complicated on the right. We got some like thing moving across the sky and like a graph. Basically, if this graph goes lower and you can see here, it goes like a dip. That means that it's less brighter. What is less brighter? The star. So the star in the back is giving off like a brightness. But whenever the planet crosses in front of the star, we can see there's a dip. That means that it's the star as we see it is a little less brighter. It's a lot less noticeable here. We can do this by kind of just looking at a light bulb. Maybe not for too long, but you can look at a light bulb and move your thumb across the light bulb, and you can then see that you can start covering up part of it, and it gets a little less brighter. So if we have these planets who are passing in front of these stars, then we can see that the brightness will go down. And that's kind of how we can figure out there's a planet in front of this star that we're looking at. Of course, this varies. If you have something that's really big, a really big planet, the dip is going to be a lot bigger. We can see this in this animation here. Here on the left, we have a planet. It's a lot bigger, and it's going across the sun. It's going to go in front of the sun here, and when it does, you're going to see that the length or this curve, it's going to be it's going to drop a lot lower. And then here on the right, we have a smaller planet. So just take a look at the difference. So around there, just going around, going around town. And as soon as it hit in front of the star, we can see that it goes a lot more of a dip for this planet than it does for this planet. So the size of the planet can make a big difference. We can on how we see this curve, so it can help us detect, is this planet big? Is it small? Is it far away? Is it close, right? So it's really great stuff here that we can use. And then extending this to of course, most stars, they have a bunch of planets around them. So if we look at a star with a bunch of planets, we'll see something a little like this. You'll take a look here. So, we have like 3 planets orbiting the sun or a star or whatever you want to say. And as soon as this big planet passes in the front, you're going to see this huge drop. And then it goes back up as soon as it leaves right now. And now we have these 2 planets are going to cross at the same time. So first it drops, and then it drops even lower because there's 2 of them. And then it drops, and then they go back up. As you can see, so it dropped a little bit, but as soon as this, oh, my bad. As soon as the second one, oh my gosh, something happened. Sorry about that, guys. Misclicked there. As soon as there's 2 in front of them, the dip is a lot more like a ladder. You have like steps going up, right? It's really great stuff. Further ado, though, this is our last method we're going to go over. This will be hopefully very short, but it's called the Doppler Shift method. It's really complicated, but I'm going to introduce this to you a little easy. So first thing we want to tell you is that light can behave like a wave. Maybe hard to understand, but just take it for now. Light can be like a little wave on a string. It's kind of, you can see here on the right. You have these like strings that are going up and down, these like waves. So that's kind of what light is, right? So if light is coming from the sun, but the sun is moving like farther away from us, we can expect the string to be pulled, right? Because if you pull a string, then it's going to get, pulled apart a little more. But if you push the string, it's going to, look like it's pushed. If the sun's coming towards us, it's going to push the string together, as you can see here on the bottom. But when you pull it, we actually notice that it gets a little red. The light will look a lot redder. Although when we push it together, the light will look a lot bluer. So why does this matter? Why do we care if the light looks bluer when it's coming towards us and redder when it's going away from us? This is because we use this in this third method here. So we're going to see there's an orbit happening here. As you can see, there's a planet orbiting around like a star or a sun. And as this planet moves around, it actually makes the sun move a little bit too. As you can see, there's another circle on the sun. It's very small, but there still is a little circle there. And because of that, that means that when you look at this system here, as the stars, oh, sorry. Once again, I had a little technical error. I tried to use, there we go. As the star is moving away from us, you can see the string's really wide. But then when the star comes right back towards us, it presses together again and it looks bluer. And now when it's going away from us, it stretches and it looks a lot redder. So if we're ever looking at a star and it becomes a lot redder, we know it's moving away from us. And if it's coming towards us again, it's bluer. So that probably means there's a planet that's making it do this weird spin. So that's kind of what we were discussing today with detecting these planets. We can go a lot more detail if you guys have any questions. I know there's a lot of information. These are really complex things. You know, astronomy is not easy, but we can all understand it for sure. We all have the capacity. And so yeah, that's a bit it for our presentation. Thank you for listening. Lister and I will be open for any questions. I'm not sure.
So there's a few questions, very interesting questions that I'm seeing in the Q&A section. So I think I can address several of them together because they are all about gravity. Well, classical mechanics, a very boring subject in physics, but very useful and explains lots of things, personal opinion. But okay, so there's a question about how a planet is going to orbit a double star system, and do all galaxies have at least one black hole in the middle? So those two questions are very interesting. So first, I'm going to address how a planet's going to orbit a double star system. So basically how a binary star system orbit around each other, it's like those two binary stars are very heavy over here and they have a center of mass, and they orbit around each other's center of mass. That's how a natural binary system works. So if you have a planet out there, the three body thing basically just orbits around the center of mass of the three bodies, which physicists calculate using a very complicated formula, but the three of them orbits around their common center of mass. The other question sort of related to this is, are there any triple star system? So there are definitely lots of triple star system. And just like how planets work, the third star would be in the outer orbit and orbiting around the center of mass of the two binary stars. But because a star is not a planet and the third star's orbit would be a bit unstable, there's ongoing complications with the three-star system, but yes, they do exist. Coming back to the question about do all galaxies have at least one black hole in the middle? So just like how planets work, okay, planets orbits around their host stars, and solar system orbits around their center of mass within a galaxy. Gravity bounds them together. So they usually orbit around a really heavy object in the center. So that object just needs to be, it may be their center of mass, it may be something else that's really heavy. It doesn't necessarily need to be a black hole, but it does needs to be very heavy. So we have a professor in Berkeley who is specializing in studying galaxies, and we're all her fans, and yeah, we learn a lot about galaxy from her. So yeah, that's my answer to those few questions, and we're also pretty happy to take any other questions.
I think also like there can be like multiple star systems, right? You don't need to have only 3 or 2. You can have like a lot more than that, right? In a system. I could be wrong. I remember learning that once, and it was pretty cool. Yeah, it seems like there's a few more questions here we can take a look at. 1 second. So I think someone asked how many light years is the closest double sun star? I'm assuming they mean like a binary, right? Where we have 2 stars orbiting each other. I believe that's Alpha Centauri, and I think that's around like 5 light years away. I'm not totally sure though. You might want to fact check me. It's around 5. It's not exactly 5. It's around 5. And I'm pretty sure it's Alpha Centauri. Hopefully I'm correct on that. But I'm not an expert in some of these distances. Astronomers don't work in light years. We actually use bigger measuring distances, like something called a parsec, which is a lot bigger than a light year, trust me.
Surprisingly, sometimes we use centimeters too, and my professor spent a long time convincing me why that's a good unit, but that's a long story. The other question I'm seeing in the chat, that's a very interesting question, is what type of planet has the coldest core? So that is a very interesting question, and the answer actually doesn't depend on what type of planet it is, but rather it depends on the pressure and gravity of the planet itself. So for a planet, we study something called a hydrostatic equilibrium. So gravity wants to pull this bunch of gas in, whereas the gas pressure of the planet wants to fight back the gravity. So the planet is in a static equilibrium. So that's why we call it hydrostatic equilibrium, which depends on the pressure and the gravity of the planet. And then gas giants are usually supported by ideal gas, whereas other type of planets are supported by electron degeneracy pressure, which is a whole different kind of pressure than ideal gas pressure, which ideal gas pressure is related to temperature, and electron degeneracy pressure is related to something else. And it is those kind of pressure support and a planet's own gravitational force that depends on how hot or cold the planet's core is. So it's a very difficult subject to go into because there's lots of thermodynamics, which is very difficult. But that's definitely something that's keeping lots of astronomers busy currently.
All right, I think we can have maybe answer one more question. I think someone asked, or let me ask at least two real quick. So one of them was asking about, is it true that our galaxy might crash into another galaxy? Yes, it's called the Andromeda Galaxy. But don't worry about it. That's a long time away, it's years away, and it probably won't really hurt us because of the way that planets or galaxies crash is not a problem. How many planets have been discovered? I think around like 4,000 exoplanets. The quick Google search, that's what that gave me at the very least. And I think, is there anything in the chat? Let's take a look. Let me see. Does the sun have enough gravity to crush human beings? Not really crush. The gravity isn't, so that'd be like a neutron star. So the neutron star would probably crush a human being. They have a ton of gravity. But a sun, it probably wouldn't crush us if we stood on it, but we probably burnt up. And I don't think you want to be on fire either. So that's something to keep in mind.
If you have nothing else to do on a Saturday afternoon, just look up the equation of hydrostatic equilibrium and then calculate the G from that and see if you can be crushed by sun's gravity.
Yeah. Also, I want to address one thing real quick. Someone in the chat said that a sun is not a good word to use when describing other stars. That is definitely true. I think there were some times where I caught myself saying sun, but I meant to say star. So I apologize for that. That was just, I guess, my bad presentation skills. But so I meant to say sun like star or like just star most of the time. I apologize for that mistake there. But most of the time we're just talking about a star in general, but the sun is a star. And most people here are familiar with the sun, so I decided to use sun most of the time because I think people understood that a lot better.